still up there. I thought you had Are you still over here? And then
Here.
other side. Are you really? 488. That sucks. No joke. What have you missed?
First three chapters up.
First thing.
Do you want us to begin in the class or
First three chapters.
no, it has two.
Just doing the homework.
Yeah, he works more with the different. If they ever found a picture, you can do that.
Only two chapters.
I had my brother come over here.
You got time. How's they get
Towards balance,
What?
put bait on the inside of it.
Oh, the crawfish?
Crawfish again.
Oh, it was real good.
Okay.
His weight. Did you go get some? Oh,
No, I saw his picture.
Where?
It's on the A-State web page.
Is it? Wait, which webpage?
Yeah, I don't know. I saw it somewhere, so I guess it's A-State.
I need to check my Twitter now.
I sat there and looked at it and I'm like,
Hashtag.
I'll just take it.
Okay, so morning everyone. So right now, this is the last example that we solved. We had this W section, okay, and it was connected through some plates at the end, okay, and we last time we calculated the strength of those plates, okay. So before we go forward, I just want to have some insight into this problem, okay. There is nothing, okay, complicated about what I'm going to say, but just, to give you some perspective about your design. So for this W section, okay, it's covered in example 3.10 over here, okay, and in example 3.6. So let's go to example 3.6, okay. So in example 3.6, this W section, okay, according to the LRFD methods, okay, it was carrying, or its strength, it can carry a load up to 488.5 K. Okay? 488.5 K. And then example 310, it was connected through a plate, okay, through gusset plates at the ends, okay, on top of the flange, on top of the two flanges, and the strength of those gusset plates are 372.9 K. Okay? So my question now, or the thing that I want to discuss with you, okay? We solved this problem correctly, okay? We have nothing wrong, okay? But what do you think of this design, using this gusset plates with this W section? What do you think of this design?
probably needs some improvement
Why? Need some improvement. Why?
because the gusset plate holds less than the.
Okay. So this design is not efficient. Even if the load, okay, that actually is applied on this. Definitely, you need to design the gusset plates so that they can withhold the load that is applied on the section. Okay. So from your structure analysis, you find the load. So probably if this is the gusset plate that you're going to be using, that means that the load that is applied is less than the 372. Okay. That's why we chose those gusset plates. But now, let's say at some extreme condition, okay, that was unaccounted for, okay, the load increased, okay, you have a larger section, you have a section that can withhold 400 and something, 480, okay, but the gusset plates are going to fail before reaching this capacity. So even if you increase, okay, you're putting a large section, but at the end you're having a very weak connection, okay, so you're not making any use of the large section that you're putting, okay. So usually, when you design, okay, your members and your connections, you try to have a consistent factor of safety, okay. Other than the factor of safety is given by the the LRFD method, the phi, the strength reduction factor, the factor of safety is in the load combination. But at the end, when you choose your section, you're not going to choose, you're not going to find the section that gives you the exact strength that you're looking for. You're going to look for a larger section, okay? So this larger section means that you're putting an extra factor of safety. You want this extra factor of safety to be as consistent as possible, okay? You don't want to have a weak part, okay? A weak part means that, all the extra material that you put in the member, okay, is just a waste, because at the end, this part is going to fail and you're not going to be making any use of this extra amount of money that you put in the member, okay? So this is just, something that you have to think about, okay, when doing your design. Some people, I saw many people, okay, that when designing, they just say, okay, I'm going to use this, it's factor of safety. Okay, that's fine, but you have to have a consistent factor of safety. Otherwise, it's not a factor of safety, you're just throwing your money, okay? So now, what we're going to do is discuss a new criteria that you have to fulfill for members under tension loads. Okay, so we said the criteria that you have to fulfill right now. We discussed two criteria. What are those? Yielding of the cross section and fracture of the critical section. The third thing that we have to fulfill is something called block shear. Okay. So now, the first thing was if you have a member like this, okay, and there is some bolts at the end. So the first criterion is no yielding at the cross section. And then the second criterion is no failure of this critical section. The third criterion that we have to fulfill, okay, it's the same member. Now, the third thing that can happen for failure here, okay, is you're applying a tensile load, okay, we're talking about members under tension, so there is a load, tensile load, P ultimate, that is applied on this member. So at failure, this section can feel like this. This part can just get torn away out of the section, okay? So if this happens, okay, this is called block shear. So this is the third criterion block shear. So what's the difference between block shear and failure of the critical section? Here, for the failure of this critical section, okay, that is over here, the entire section is under tension, okay? While here in block shear, for the block shear, let's see here, for block shear to happen, taking this green section out, okay? For this to get broken or torn out, okay, there will be some tensile stress applied on this surface, okay? So this is tensile stress, and for this other surface to break down, there is a shear stress. So you actually have this tensile force, P ultimate, resisted by some tensile stress and by some shear stress, okay? Once the capacity of the shear strength along the shear surface and the tensile strength of the tensile surface is less than the applied load, then this part is going to get, torn out, okay? So we have two parts here, okay? So now, the area here for the shear stress, we're going to call this AV. This is the area of the shear surface, okay? And the area here for the tensile surface, we're going to call this AT, the tensile area, okay? So this failure, the block shear, okay, is covered by the AISC in this section. So covered in the AISC, it's not covered in chapter D of the specifications for the tension. It's actually covered in section J4. Section J is for general provisions. So it's covered in section J4.3. Okay? So how much is the strength of those two surfaces altogether? Okay? How much load it can resist before it fail in the block shear? Okay? So the design equation for block shear failure that is given in section J4.3, it states that the nominal strength of those two surfaces is the summation of the nominal strength of each of those surfaces separately. So you have some factor of safety 0.6 F ultimate for area net shear, okay, plus some factor UBS multiplied by F ultimate area net tension. Or there is another equation, so you have to fulfill both equations. It's 0.6 F yield area gross shear plus the same factor UBS F ultimate area net tension. This is equation J4.45, okay, J45 in the AISC, okay. So this is the nominal strength for block shear, okay. As you see, it's the summation of two terms. One is the strength of the shear surface, and the other is the strength of the tensile surface, okay. So this is the nominal strength. What about the ultimate strength or the allowable strength for LRFD and for ASD? You just have to multiply by phi for LRFD, and phi in this case is 0.75. And for ASD, you have to divide by omega, which is going to be 2. Okay? So now, what are the terms in these equations? A and V is the net area in the shear direction. AGV is the gross area in the shear direction. A and T is the net area in the tensile direction. We know what's Fu, this is the ultimate strength of the steel used, and Fy is the yield strength of the steel used. The other factor that we have here is the factor UBS. So the factor UBS, this is a uniformity factor depending on the configuration of the bolts. So how much is UBS? We have two cases. So if the connection looks like this, so when you have block shear happening, this part would be torn away, okay? So you have P like this. In block shear you have shear surface, a tensile surface that's going to fail together, okay? So this part is going to get torn away, okay? So here for the tensile surface, if the tensile surface, okay, is not blocked by any holes in front of it, okay? There is no holes in front of the tensile surface, okay? Those holes are at the edge of the tensile surface, then in this case, UBS is equal to 1, okay? So here, the tensile surface is not blocked by bolts. While you can have a connection that looks like this, so when block shear happens, this part is going to get torn away, okay? So when this happens, okay, as you see here, the tensile surface, this is the tensile surface, it's blocked by, you know, there are some bolts in front of it, okay? So in this case, UBS is equal to 0.5, okay? So that's how it's going to feel, okay? And this is the factor of safety here is 0.5, okay? So now, let's see some examples. So, example 311. So, example 311 states that the A572 grade .50 tension member shown is connected with 3/4 of an inch bolts. We're required to find the LRFD design inside strength of the member. So how does the connection look like? We have angle this angle is L 6/4 by ½ inch. It's connected at the end to some plate, okay, and this length, this leg is 4 inches, and the other leg over here is the 6 inches. Okay, and it's connected through bolts at the end here. Okay. So the top view, so this is a front view of the section. Top view, we have the angle. Two legs of the angle, and it's connected to that plate. So here we have 1, 2, 3, 3/4 of an inch bolts, and those dimensions here. We have 2 inches, 4 inches, 4 inches. Okay? So this is how the connection look like. Okay? So now what we want to do is to see how much force can this member resist. Now we're adding an extra criterion that we have to satisfy, the block shear. Okay? You cannot check the block shear without having the edge distance, this edge distance, given. If it's not given, then you're not going to be able to check for the block shear. Okay? So now we want to solve or check this section, see how much force it can resist. So how to do this? Exactly the same, or just the same like last time. We're just adding then an extra, check or an extra calculation that we have to do. So the first thing that we have to do is the yielding of the cross section, and then the failure of the critical section, and then the extra part that we're going to do today is the block shear. Okay? So to do those calculations, we need to find the properties of the material used and the properties of the section. Okay? So in this problem, it states that we're using A572 grade 50 steel. So for the A572 grade 50 steel, we need to find the properties of that section. How can we do this? Where do you find this? You go to chapter 2, the general section. Okay, so chapter 2 here, general section. And then at the end of it, we have those tables, table 2, 4. We're looking for A572. It's over here, A572, and then grade 50, okay? The F field is 50 KSI, and F ultimate is 65 KSI. So going back, so it's not showing here. It's showing for you, but it's not showing for me. My screen is dead. So how can I still nothing.
Try unplugging it from the tablet, plugging it back in.
Hmm?
Oh, it's working.
It's not working. I cannot see
Try
it.
unplugging it from you're using your tablet.
No, I'm not using the tablet. I'm using this computer. Yeah, it will take like 10 minutes.
This is the screen. I was seeing if it was connected. If it got
You see, it's already there, you know.
Where's your power button? This isn't the power button.
Yeah.
Well, the monitor's on. I was thinking you could turn.
Okay, I'll have to go call them. Okay, I don't want
Okay, the teacher.
You're not fully protected, man.
Oh no.
cannot see myself, so I cannot talk. Working on it. See myself on my computer here. So I cannot write, you know, I cannot see anything.
You probably have to.
Yeah, the screen's popping up, so I taped it down, so it's staying on.
Okay.
Home button will get
Now, yeah, we'll just do it.
Need an upgrade. Oh, yeah.
They like a free trial to download this.
I just logged for like what they put. I'm doing a duplicate, but it's not working.
Yeah. Sometimes it's the L mode that can.
It's going to sleep. Now,
Okay.
Yeah, it's not.
It's
now
gone.
It's going to sleep, yeah.
Try the
I have
duplicate now.
tried the duplicate, I have tried the duplicate, but it's not. You can enter password.
Oh. Okay. Yeah.
Okay, yeah.
So sometimes if that happens and you can do the Windows P, try just unhooking those and put it back in.
Okay. Thank you.
Got it.
So now for this grade of the steel. So from table 2.4, we expect the value of F yield. It's 50 KSI, and F ultimate is 65 KSI. So now we also need to find the properties of this angle. Okay. So it's 6 by. Yes.
What page was that table on?
248. So this is page 248. Okay. So now we also need to extract the properties of the L6 by 4 by 1/2. Okay. So what properties do we need here? Okay. We need the area. So now we need this distance, right? Whatever we're gonna call it, X bar, Y bar, depending on how it's gonna get oriented. Okay. So we're looking also for this distance. What else do we need?
Gross area. Or gross area, excuse me.
There is some extra thing that we need. Okay.
Gross
Okay,
area.
the thickness is 1/2. Okay. What else?
Area cross.
Area cross. Yeah, we mentioned that we need the cross area. The location of the bolts. Okay. The location of the bolts is not given, so where will we find this? We have the table that give us the gauge line. Where's the gauge line? Okay, where's the location of the bolts? So that's also something that we need to find. So for the L6 by 4 by 1/2, let's go back. Hopefully we're not going to have any problems. So going to table 1.7 for the angles, we're looking for L6 by 4 by 1/2. So 6 by 4 by 1/2. It's over here. This is page 146. Okay. So it's over here, L6 4 by 1/2. We have the area equal to 4.75. Okay. So that's the area over here, 4.75. That's what we're looking for. And also we need the distance, X bar, okay, to calculate U. So is it X bar really or Y bar that we're looking for? So actually the distance that we're looking for, it was the location of the centroid in the long leg, in the short leg, okay, the 4 inches, okay? So here it's actually this distance, X bar. So that's what we're looking for, X bar. So L6 by 4 by 1/2. So X bar is 0.981, okay? So that's what we're looking for. So let's write those. And then, so the area gross is 4.75 inches squared. And the distance X bar, okay? So although I'm calling this X bar, although it's a vertical distance, okay? So X bar is 0.981 inches, okay? And then also we need the gauge distance. So those are from table 17, page 146. And then the gauge distance. So the gauge distance is the location of those bolts, okay? Where's the location of those bolts, okay? So those bolts are in which leg of the angle? The 6 inches long, okay? So this, to find the gauge line, you go to table 17A here. So table 17A, the leg is 6 inches, right? And we only have one bolt, okay? So we're looking for this distance G. So the distance G is 3.5 inches from the back of the angle. As you see here, G is measured from the back of the angle. So G for 6 inches, the gauge line is located at 3.5 inches from the back of the angle. So that's table 17A on page 142. So 3.5 inches from the back of the angle. This is table 17A on page 152. Okay? So now that means that this distance is 3.5 inches. So how much is this distance? 2.5 inches. Why am I so interested in this distance?
Small area.
So for block shear, this distance is so important because for block shear, this part is going to get broken out, right? So the length of the shear surface is the 2.5 inches, okay? That's why I need to know this distance, okay? So for block shear, this is going to get, torn away. So now once we found all those properties, now we can start doing our, checks for the 3 criteria that we have. The first one is the yielding of the gross section. So that's normal, P nominal is area gross, F yield. So area gross is 4.75 inches squared. F yield is 50 ksi over here. So multiplying those, this is 237.5 K. Multiplying this by phi to find the ultimate strength. So phi is 0.9 for yielding, multiplied by the 237.5 K. So the maximum force that can be, resisted in this member before yielding happens is 213.7 K. Okay? And then the second thing that we need to check is the fracture of the critical section. So for the fracture of the critical section, we need to find the net area. How much is the net area? It's the gross area minus the area of the holes, plus S squared divided by 4GT if we have an inclined line. Do we have any inclined lines? Do we have any staggering? No, so that's it. So area gross is 4.75 inches squared, and then the area of the holes. How many holes do we have per critical section? Just one. So the area of the hole is equal to the diameter of the bolt plus the clearance. The diameter of the bolt is 3/4 of an inch plus the clearance, which is 1/8 of an inch, multiplied by the thickness. How much is the thickness? It's 1/2 an inch. So this is going to be 4.31 inches square. That's the net area. Now we need to calculate the effective area by multiplying this net area by U, the shear lag factor. Okay? So to calculate U, okay, we have to go to table D3.1 and see what cases apply. Okay? So U, let me go here, U, the shear lag factor. On table D3.1, is it D3.1 or D3.2? So chapter D, D3.1, yes. So here for table D3.1, okay, we have which cases apply here. We have case 2, okay, because it's only connected through one of the legs, okay? So U is 1 minus x bar over L, and that's an angle. So here in case 2, it states that case 8 is permitted to be used. So per case 8, it says with 4 or more fasteners per line in the direction of loading, then U is 0.8. We don't have 4 or more. For 3 fasteners per line, that's the case that we have, U is 0.6, okay? So let's calculate U per case 2 and compare it with the 0.6 from case 8. So for case 2, U is 1 minus x bar over L. So 1 minus x bar. How much is x bar? We extracted this value from the table. It's 0.981 inches divided by L. How much is L? It's the distance from the first to the last hole or bolt. So L is 8 inches. That's 8 inches. So U is 0.88. Okay? And then for case 8, U is 0.6. So which value should we use? The larger value. Therefore, use U equal to 0.88. So now the effective area is U multiplied by the net area. U is 0.88 multiplied by the net area, which is the 4.31 inches squared. So that's 3.79 inches squared. So now just multiplying this effective area by the ultimate stress of steel. So we're going to get the nominal strength of the section, 3.79 inches squared, multiplied by the ultimate stress, which is 65 ksi. So here we have 246.4 K. And then multiplying this by phi, the strength reduction factor, we find the ultimate stress, or the ultimate strength, the strength of the member. How much is phi? 0.75. So multiply by this nominal strength. So this member can only hold 184.4 K before failure of the critical section. All what we did is this repetition of what we did earlier, okay? The new thing is the block shear. We also have to make sure that our section doesn't fail in block shear. That's the new thing. Okay? So for block shear, the angle looks like this. We have 1, 2, 3 holes in block shear. What will happen is it's going to fail like this. This part just get thrown out. Okay? P. So now for this section to break out, okay, we have here we have a shear surface, and here we have, sorry, this is the side surface, and here we have a shear surface, AV. Okay? So the strength of the section here depends on those areas, AT and AD. Okay? So in the equation we need to find AT, the net tensile area, and for the shear area we need to find the gross area and the net area. Okay? So let's start finding those one by one. The net tensile area. So for the net tensile area, how much is the net tensile area? Here, the net tensile area is the width of this section, which is how much? 2.5 inches. Okay, we got this from the gauge line, the distance of the gauge line. So we have 2.5, okay, multiplied by the thickness. That's the gross area. But actually, you have to subtract 1/2, because here, this part is not in the tensile area. Right? You have the bolt, okay, that is getting subtracted from the area, but not the entire bolt, okay? Because the distance 2.5 is measured to the middle or the center of the hole, okay? So actually, I just have to use 2.5 minus, okay, 1/2 the diameter of the hole. The diameter of the hole is 3/4 of an inch plus 1/8 of an inch. So that's the width. And then I have to multiply this by the thickness of the angle, which is 1/2 of an inch. Okay? So that is equal to 1.03 inches squared. Any question regarding this calculation? Okay. So, and then we also need to find the area gross for the shear surface. So how much is this length? The length of the shear surface. It's 4 and 4, and the edge distance is 2, so that's 10 inches. Okay? So we have 10 inches multiplied by the thickness, which is 1/2. Okay? So this is 5 inches squared. That's the gross shear area. And then we need to find the area net for the shear surface, which is the 5 inches squared, the area gross. This is the area gross in shear, minus the area of the holes along that surface. So this is 5 inches squared, and then minus the area of the holes along that shear surface. How many holes do we have along that surface? How much?
1.5.
1.5? No.
Just one.
No. No. 2.5. This is 1, 2, and then 1/2 here. Okay? That's what you're subtracting from this surface. Okay? So minus 2.5 holes. We have 2.5 holes multiplied by the area of each of those holes, which is the diameter of the hole multiplied by the thickness. So the diameter of the hole is 3/4 of an inch plus 1/8 of an inch multiplied by the thickness of the angle, which is 1/2. Yes?
If you're going to consider the hole, would it just be a quarter that last hole?
No, let me. So you have 1, 2, 3. Okay? You have this line here. This is the shear line, right? It goes up to the center of the hole here. So this is 10.
What about the other direction, 18?
Okay, now talking about the shear surface, not 80. 80, we already calculated the area for 80.
No, what he's saying is, why are you subtracting a whole half a circle when it's only going to the center, so it'd be only a quarter circle?
Okay.
It's in one direction.
How much is this distance? 1/2. Okay, it's not 1/4. Okay, I'm subtracting. Yes. Okay, this is what you're talking about, a quarter over here. But this quarter, okay, I'm subtracting 1/2 from the shear and 1/2 from the tensile.
Oh, okay.
Right? You got it? So, so this is 1, 2, and a half here. Okay. So now this is going to be equal to 3.91 inches squared. For the equation that we're looking for, okay? Let me show you the equation in the block shear so that you can highlight this, so use it on the test. We're going, it's not in chapter D, okay? It's not in the tensile chapter, it's actually in chapter J, okay, of the specifications. So J4, so you go to the specifications over here, okay, specifications, and then we're gonna go to chapter J, okay, design of connections over here. So for chapter J, J4 here, it's for block shear. It's over here on page 16.1, okay, 138, okay. So this is the equation for the block shear that we're looking for, okay. Phi and omega that are used with this equation. This is the equation. It's 2 parts, okay. So UBS, we need to find UBS as well. We find already area net shear. Let me zoom a little bit so that you can see this more clearly. So area net tension, and here we have area gross shear and area net shear, okay? We need to find how much is UBS, okay? So this is equation J4.5, okay, that we're looking for the block shear. So now, how much is UBS? So for UBS, for the tensile surface, there are no holes in front of the tensile surface. So that means that UBS is equal to 1. Okay? Now I can go ahead and start applying those equations that we saw. The equations read like this. The first equation is 0.6 F ultimate area net shear plus UBS F ultimate area net tension. The second equation is, they look pretty much the same except for the first term. Instead of multiplying by F ultimate, it's F yield, and then this becomes area gross shear, and then the second term doesn't change. Okay? So applying the first equation, we have 0.6 multiplied by F ultimate, which is 65 KSI. Area net shear, that's the 3.91 inches squared that we just calculated. UBS is 1. F ultimate is 65 KSI. And then area net tension, the area net in tension is 1.03 inches squared. So from this equation, P nominal is equal to 219.44 KSI. K. Kips. Okay? For the second equation, it says 0.6 F yield, which is 50 KSI, multiplied by the area gross for shear. Area gross for shear is the 5 inches squared, plus UBS, which is 1, multiplied by 65 KSI, multiplied by 1.03 inches squared. So that is equal to 216.95 K. Which one of those two controls? The 216. So therefore, P nominal is the 216.95 K. That's the nominal strength. I need to find the ultimate strength by multiplying by the strength reduction factor. How much is the strength reduction factor for block shear? 0.75. Multiplied by this P nominal. So the ultimate force that can be resisted by this member is 162.7 K. So now we have three numbers. The maximum force that can be resisted so that yielding doesn't happen is 213.7. So that fracture doesn't happen, it's 184. So that block shear doesn't happen, it's 162. So which one is controlling the capacity of the section? The smallest one. This is the governing value. So this section is going to fail in block shear before anything else can happen. So this is the one that governs.
How did you find the area net shear? I didn't see it write that. I'm not writing that wrong or something because I might get 1.0.
Okay, so the area net for the shear is this vertical, the area of this vertical line, right?
Okay.
So how much is the area? It's the length multiplied by the thickness. Okay?
Okay.
If I multiply the length by the thickness, that's the gross area. Okay? So the gross area is the length, which is 10 inches, multiplied by the thickness of the angle, which is half an inch, so that's 5 inches squared. That's the gross area of the shear. The net area is where I have to subtract
Not sure, I'm at tension.
this diameter and this diameter.
Tension. I'm at tension, I didn't mean shear.
Hmm?
I'm at tension, not shear.
You meant tension. Okay,
Yeah.
so for the tension, the surface that is under tension is this horizontal line over here. This is under tension, right? So again, the gross area of this line is the length of the line, which is 3.5 inches, or 2.5 inches, okay? Multiplied by the thickness, okay?
That's one.
And then I have to subtract, this is the gross area of the tensile surface, and then I have to subtract the area of the holes. How many holes do we have here? Just half a hole, okay? That's why I'm subtracting 1/2, and then the diameter of the hole multiplied by the thickness of the angle. Okay? So that's the area net tension. Yes?
One's the equation of inequality, but it's, I mean, it doesn't.
So
it's
the
not
equation-
directly equal to, it's actually opposite.
The equation here,
Yeah.
so this is actually like you have to calculate Rn
Right.
from the first part, okay? And calculate it from the second part, okay?
That equation's false, though.
Is what?
It's false.
False?
It's saying that the left is less than or equal to the right.
No, it doesn't say that the left is less than the right. It says that the left has to be less than the right. If it's not, then you're going to take the right part of the equation.
Okay.
You understand what I'm
Yeah.
saying? It's not stating that the left is less than the right. If the left is always less than the right, then why would you calculate the right part of the equation? Okay? It says that the left has to be less than the right. Okay? If it's not, then you're going to take the right value, not the left value. Okay? Any question here? Okay, that's good. So let's see another example here. This example, it's in the textbook, but I see it as a very poor example, but we're going to go through it so that we cover everything in the textbook. Okay. In this example, we have a plate here. Okay. This plate. Okay. There is a tensile force, PA. So we're using LRFD, and there is another plate connected to it. And they are connected through welds, longitudinal and transverse welds. So this is PA. The width of this plate is 10 inches, okay? And this length, the length of the weld over here, is 4 inches, okay? So this plate is 10 by 1/2, okay? So the width is 10, the thickness is 1/2 an inch. So what we're required to find here is the ASD, allowable strength of the A36 plate shown. So for the solution, we need to check the 3 things, okay? First, we need to find the properties of the A36 steel, so this is through table 2.4, okay? So for A36 steel, the F yield is 36 KSI, and F ultimate is 58 KSI. And then we need to check the 3 things: yielding of the cross section. So how much is the area gross? 10 times half. So we have 5 inches squared, and then the P nominal is this area gross multiplied by F yield. So it's 5 inches squared multiplied by F yield, which is 36 KSI. So it's 180 K. And then we're using ASD, okay? So for ASD, the allowable force is this P nominal divided by omega. So we have 180 K divided by omega, which is 1.67. So the maximum force is 107.8 K. Okay? And then the second thing that we need to check is the fracture of the critical section So for the fracture of the critical section, we need to find the net area. How much is the net area? It's the area gross minus the area of the holes. There is no holes, so the area net is equal to the gross area, which is the 5 inches squared. And then we need to find the effective area. How much is the effective area? This net area multiplied by U. How much is U? You go to table D 3.1. Which case in table D 3.1 you think it will apply for this section? The first case, the load is transferred. You only have one element here. It's just the plate, and you have welds all around the section, right? No, you have longitudinal weld and transverse weld. Okay. Case 2. Okay. If you have I guess case 2.
Either or and in combination of case 2.
Okay, let's look for the table here. So in the table over here, case 1 says all tension members where the tension load is transmitted directly to each of the cross-sectional elements by fasteners or weld, except case 4, 5, and 6. Okay. Case 2 doesn't apply. Case 2 here says by if it's transferred through an part of the elements, not all the member. Okay, so case 2 doesn't apply. Okay, so 4, 5, and 6 for 4, case 4, you only have longitudinal weld. 5 and 6 is where you have hollow structure shape, so they doesn't apply. So actually, it's case 1 that applies. So U is equal to 1. Okay, so the effective area is equal to the net area. Okay, there is no reduction, or the section is all effective in transferring the load. Okay, so per case 1 in table D3.1, U is equal to 1. So the effective area is U minus area net, so they are equal to each other. It's 5 inches squared. So now we have this effective area, so the nominal strength is the effective area multiplied by the ultimate stress. So the effective area is 5 inches squared multiplied by the ultimate stress, which is 58 ksi. So this is 290 K. And then we need to find the allowable load, which is the nominal strength divided by omega. So we have the 290, and omega for fracture is 2, so this is 145 K. And then the third thing that we have to check is block shear. Okay? So this, for block shear, we have this section, right? Just keep going down. We have our plate like this. It's connected to the other plate here. So they are connected by weld, okay? For a block shear, okay, that's so close to the failure of the weld, but not the weld itself. Maybe the weld has a higher thickness, but the plate itself fails here. The plate itself gets torn like this, okay? It's not the failure of the weld, that's something else, okay? We're not studying the connection, okay? The weld or the bolts, the strength of them. We're studying the member itself, the strength of the member. So if the member fails here, that's block shear. So how much is the strength of this line that we're showing, okay? So now, for this line, okay, we have part, so this is the load applied like this, tensile force. So this tensile force is going to be resisted through shear and tension. Which surfaces are under shear and which surfaces are under tension? The two that I'm showing, those are under shear. And this one in green is under tension. Okay? So now we can go ahead and calculate the area, the required, values for the equation. Area gross for the shear, area net for the shear, area net for the tension. How much is area gross for the shear? How much is this distance? 4 inches, but we have 2 shear surfaces, okay? So we have 4 times 2, okay? Because we have 2 shear surfaces, 2 shear lines, multiplied by the thickness, which is 1/2. So 8 times 1/2, that's 4 inches squared. And then how much is area net shear? Are there any holes? No, so area net shear is equal to area gross shear, so that's 4 inches squared as well. And then area net tension, area net that is under tension, how much is this width? It's 10 inches squared, 10 inches, So we have 10 inches multiplied by the thickness of the plate, which is 1/2, so we have 5 inches squared. Okay? And how much is UBS? There is nothing blocking the tensile surface, so UBS is 1. And now let's apply the two equations. So the first equation, it says 0.6 F yield, area gross shear, plus UBS F ultimate, area net tension. So 0.6 multiplied by F yield, which is 36 KSI, multiplied by area gross shear, which is 4 inches squared, plus UBS, which is 1. F ultimate is 58 KSI. Area net tension is 5 inches squared, so that is equal to 376.4 K. Okay? And then the other equation, it says 0.6 F ultimate, area net shear, plus UBS F ultimate, area net tension. So that's 0.6 multiplied by 58 KSI multiplied by the 4 inches squared, plus UBS, which is 1, multiplied by 58 KSI multiplied by area net tension, which is 5 inches squared, so that's 429.2 K. So now, which one of the two equations governs? The top one. So P nominal is the smaller value, the 376.4 K, and then I have to multiply this by the factor of safety or divide by actually omega. So Pn divided by omega, so 376.4 divided by omega, omega is 2, so this is 188.2 K. So now we have three values. For yielding, it's 107.8. For fracture, it's 145. For block shear, it's 188. So which one governs? Yielding. So yielding governs. So therefore, PA, the maximum force that can be held by this member, is 107.8 K. That's the answer. So when I started solving this example, I said that this example is a very poor example. Why?
All the areas are kind of the same.
Okay, that's one thing. And then when comparing block shear to the structure of the critical section, the block shear area, okay, is higher. It's so clear for everyone that the block shear area is higher than the area of the critical section. For the critical section, you only have, you know, the vertical or the section or the line under tension. You don't have the shear. So actually, block shear is not so obvious for anyone that block shear is not going to happen. Okay, the critical section, failure of the critical section might happen. Okay, but definitely block shear is not something that you would consider for some connection like this. Okay, so that's why I feel it's not a very good example, but it's in the textbook, so we solved the same way the textbook did. But I guess for an engineer that have some insight, I wouldn't check the the block shear at it. Okay, any question? Okay, thank you. So again, one thing also about the homeworks. Okay. The TA who's grading the homework says, I never worked with him before, so if you have any questions about how your homework is graded, if you feel there is any problem grading it, let me know, okay? Jane? David Murphy, is David here?
You haven't put any of the journal stuff on Blackboard.
Just write down while you're here so that I don't forget.
There's just a couple days that that day that I was sick, and then that day that I was just gonna watch, but
Oh, you know, the thing is, you know,